or at least a near almost collision. Another great little pair, but again, there's no collision here. Both of these galaxies look pretty normal. And this guy's in the foreground, the guy who's face on, and the more nearly edge-on galaxy is clearly in the background. And they're probably separated by a good 6 or 7 or 8 or 10 galaxy diameters, if not more. Now, they might end up colliding sometime in the future. Wouldn't be surprised. But not yet. Okay, so if they don't look disturbed, because they're fragile, see, when two galaxies don't, this is like a drive-by, a hit and run here. And what's happened is these are stars that have been yanked off from this guy and from this guy. Tidal tails. Tidal tail here. And while the tidal stretching is in this direction, there is tidal compression in the perpendicular directions. And the compression amplifies the density and helps initiate star formation. So when you see blue here, you should think, oh, these are hot young stars. Young and hot. Hot stars. Which are always young because hot stars live short lives, just a few million years. So this is all starbursts that have happened due to the passage of this guy and this guy next to each other. So one of these is, well, they're both slinging right by each other. Another example, same thing, blue tidal tails lit up by massive hot stars. Ring galaxies, kind of like shells that we talked about before, evidence of a central collision. Now, I don't know who initiated this. I don't think it's this guy. This guy looks too undisturbed. This looks like a normal spiral, barred spiral galaxy. Maybe this guy. Ellipticals are hard to mess up because they're already totally blendered. Maybe this guy is heading this way. I'm taking a guess here. Maybe it was somebody else I don't see. Maybe he's still in here and just merged again. You know, sometimes these guys come in and then they go back and then they go in and they gradually just mush together and become one galaxy. Polar galaxy, same thing. Polar ring galaxy. And you see what the collision does to the central bulge. It stretched it out into a peanut. So there's a collision here that has clearly been in this perpendicular direction like that. And as it's pulled in, the gravity of the second galaxy, when it's now here, pulls material in here that used to be in circular orbits. It gets pulled in, and then you form a polar ring. Okay, so now we're going to talk about how elliptical galaxies form. Here's an elliptical galaxy. Basically, they're just blendered galaxy collisions. So my analogy is like my morning smoothie that I did about an hour ago. 2 hours now. And what's going on there is the galaxies collide. But because they're so fragile and the stars are not rigidly attached to each other, they're just sort of weakly gravitationally bound, it's really kind of like thinking of atoms in a gas. The atoms are like the stars, and the gas is the galaxy, because there's 100 billion stars, and that's enough to really make it look like a continuous fluid. And I wish I could show you a YouTube, but I'm sure you can find YouTubes on the web that will show you galaxies in collision in numerical simulations that are pretty accurate. And they'll show you how the galaxies just sort of merge together and settle in. And as they blender together, I mean, okay, so like my morning smoothie, I first throw in a banana and an apple, and you can tell that it's a banana and an apple. And even a half second after I've turned on the blender, it still looks like chunks of apple and chunks of banana. But after a few seconds, you can't tell anything because it's all blended together. You have no idea what fruit I threw in. It's all just a complete blended mess. All regularity, all detailed structure has been blended away, and now they just look like a smooth conglomeration of stars. And all structure is gone. That's what elliptical galaxies are. Now, they're not round. Some are, but most aren't. And we looked at these and we thought, well, this is back 40 odd, 50 odd years ago, and we didn't know. We didn't have the technology to really tell, and we thought, well, gee, these are probably rotationally flattened. That's our guess. They're probably rotationally flattened galaxies. So if they're rotationally flattened, then the equator is bulged out by the rotation, and the poles are pulled in. And an object like that is an object that is like a hamburger bun, and that kind of shape geometrically is called oblate. So that is an oblate object. A prolate object is one that is the opposite. It's got two equal dimensions and then a longer one. That's like a hot dog, not like a hamburger bun. And then there's a third possibility for how you would make something that looks oblong on the sky, and that is that it has three different lengths for its three principal axes, and that we call triaxial. So which were ellipticals? Are ellipticals prolate? Are they oblate? Are they triaxial? Well, our first guess is that they were oblate because we figured they were oblong because they're rotating, just like spiral galaxies are a little bit oblate because they're rotating. But we were wrong. So how do we figure out we were wrong? Here's what we noticed. That the outlines of the galaxy were not along the same orientation. The inner parts of the galaxy are oriented one way, and succeedingly fainter outer parts are oriented with an axis that twists. And the outermost parts of the galaxy are oriented perhaps more like that. They show what we call twisted isophotes. Isophote being a curve that joins together areas of equal surface brightness. So these oblate objects and prolate objects could be then observed. You could make them in a computer. Just use a random number generator, but put in a probability distribution that is consistent with being oblate or being prolate, and then make a few hundred million stars, or at least a few million stars, and distribute them according to that probability distribution, and then, quote, observe it, unquote, by projecting it onto a flat plane, a two-dimensional thing, as we have to do when we look at galaxies projected on the sky. And when we did that for oblate objects and prolate objects, they did not show twisted isophotes. But elliptical galaxies do show twisted isophotes, and that's what triaxial objects do. Ergo, ellipticals are triaxial. You should remember that. Ellipticals are triaxial. They are oblong not because of rotation, but because they are actually merger remnants of collisions. The galaxy collisions are common. We just talked about that. Here's a numerical simulation of three galaxies colliding together. So we start out at an early time, and then we go forwards in time, and they begin to merge, and for a while they look like a mess. So this galaxy you would classify, if you saw it on the sky, as an irregular. Doesn't have any particular shape. But if you just wait a little longer, then it's going to look like that, and that we would classify as an elliptical. Early on, this looks like a spiral. So you can take three different spiral galaxies, throw them all together, and the wreck that ensues and blenders together is going to look like an elliptical. You could merge three spirals, you could merge three ellipticals that still look like an elliptical. You could merge an S0 and a spiral, and that would be this. You could merge together an elliptical, an S0, and a spiral, and you'd still get this. It doesn't matter what you start with. You are going to get this in the end. Okay? You can't tell what fruit I threw into my blender. After a few seconds, it all looks the same. That's the key. Here's a whole different simulation. What do you get at the end? An elliptical. That's the origin of elliptical galaxies. They are merger products. And here's a compact group which is going to become an elliptical. This galaxy here you would classify it as irregular at the moment. That irregular. This kind of looks, it's still got a spiral disk outlined by this dust lane. But I don't know. It's starting to look pretty irregular. This I would still call a spiral. But anyway, these guys are all going to merge together and be one big giant mess. It's going to get smaller and denser. And it's just going to be a giant elliptical galaxy. Got to wait a couple of billion years, but it'll happen. Classic Stephan's quintet. Beautiful little cluster, tight little cluster of galaxies. Clearly this spiral has already gotten highly disturbed. These guys are both highly disturbed, tidal tails pulled off. This guy still looks normal. This guy already looks blendered. This is an elliptical or an S0, a little hard to tell. But these guys are all going to merge together and make one big giant elliptical. Just got to wait another billion years or so. Okay, now we talk about S0s. Okay, so let me summarize first of all. We've now understood how we form spirals. Little protogalactic clumps joined together. The stars that are in them cannot dissipate their energy, and so they remain in these roughly spherically distributed orbits, and that's how you get the central bulge. Stuff falling in late from gas forms the gas disk, and then the disk of gas slowly forms into stars, and the stars inherit the motion of those stars, of that gas. Ellipticals form from collisions. Irregulars are just intermediate stages in the collisions of galaxies. And barred galaxies are just spiral galaxies that have a region where the rotation period is the same for a whole big range, and therefore the arms are straight. They have solid body rotation. Okay? Quick summary of what we just did for the last hour. What about S0s? Where do they come from? Okay, so now imagine a spiral moving through the intergalactic medium, the space in between the galaxies within a rich cluster. A rich cluster of galaxies might have hundreds, might even have 1,000 galaxies all in a big pile. We'll see those a little more later. Okay, there's gas in the disk of the spiral, but there's also gas inside the cluster. In fact, the cluster might be most obviously seen by its galaxies, but yet if you could really take a proper census of what's in there, you would find that roughly half of the ordinary matter in that cluster is in the form of just gas, a medium of air, for example, that the galaxies are moving through. And the medium can be relatively denser or relatively less dense, depends on its age and how rich it is. But it's possible for the density of that gas, especially deeper towards the middle, for spiral galaxies that are moving through it to actually have the gas in the spiral get blown right out. So we call that ram pressure stripping. And the analogy is, imagine smoking a cigarette inside your car, and your car is a convertible like we used to have in the old days, and you pop the top on your convertible, and now, of course, as you're going down the freeway, the ram pressure of the air is going to blow the smoke right out of your car. And that's what's happening. Now, once the gas is blown out, you've gotten rid of all the raw material out of which you could hope to make new stars in your galaxy. It shuts off star formation. Star formation in your spiral galaxy shuts off. And the massive blue stars that outline the spiral arms quickly die because, again, they live short lives. And the spiral arms fade away. And what are you left with? You're left with a galaxy that has a disk, but it doesn't have any spiral arms. These spiral arms have all faded away because star formation was shut off hundreds of millions or maybe even billions of years ago. And the structure overall remains, but the spiral arms, which are much more ephemeral, have faded away. And that's all a nice story and common sense and fits really well. But how would you really confirm it? The way you confirm it is you look for where you see these things. And where you see them is in rich clusters. You don't see them all by themselves in the middle of nowhere. You see them in dense environments where there is a lot of intercluster medium and they can get stripped of their gas in the way I just described. The same reasoning would apply to trying to figure out how ellipticals form. Of course, you can do it in a computer and be pretty convinced that you got it right. But you can secondarily confirm it because they are indeed more common in rich galaxy clusters. So are irregulars, where collisions are going to be more common. You get more collisions if you're in this inner city like New York City and you're not careful than drivers who are similar level of care in their driving, but way out in the sticks somewhere. Okay? Pretty common sense. Galaxy evolution of colors. They start out blue, and then they end up going to red. So the evolution of galaxy colors, they start out blue because they're dominated by massive blue stars that live short lives, and then they die, and then the stars that haven't died are eventually going to become red giants, and they're the brightest. They're as bright as blue giant stars, and so old stellar populations are red, young populations are blue. Okay, so galaxy collisions lead to irregulars. Irregulars settle down and become ellipticals. And so that's it for normal galaxies. And let me just make sure I covered all the stuff I need to. So prime distance indicator again for galaxies is Cepheid variable stars. You should remember that. The most accurate way to measure the distance to nearby galaxies, Cepheid variable stars. Elliptical galaxies show twisted isophotons, and therefore they are triaxial. We live in a poor cluster. A big galaxy in a poor cluster. Big house in a small neighborhood. Okay, so now active galaxies. So that's an interesting story, kind of fun. So let's try and go through that quick. Looks like I'm going to use up the whole hour and a half. You know, once I get going, it's fun to just share everything I know. And sorry, I told you this is going to be short, but I guess it's not. Okay, so in the 1940s, Carl Seifert identified a class of spirals that had an additional feature, and that feature was that they had bright star-like cores. Bright star-like cores. Those came to be called Seifert galaxies. Then, shortly after, we found elliptical galaxies that also had bright star-like cores. We call those BL-lac objects because the first one that was identified, we misclassified it as a variable star. And we only realized later it was an elliptical galaxy far away. And the variable stars are named like this. 2 letters and then the constellation that it's in. This is Lacerta, the lizard. BL-lac. BL-lac